Hello, my name is Kiran Kumar. I am a physics lecturer. Today topic is apparent depth, real depth and apparent normal shift of the glass slab. Please watch my previous videos part 1, part 2 and part 3. This is the part 4 video. So here light traveling from the rarer medium to denser medium. Here, the glass slab takes place between the object and the observer. Observer is very close to the rectangular glass slab. T is the thickness of the rectangular glass slab. Now, observer in a denser medium and object in a rarer medium. Then corresponding formulas already we did in the previous video. Now I am writing directly formulas. Now this is the apparent depth which is equal to mu into real depth. Try to understand. Here real depth which is equal to apparent depth divided by refractive index and apparent normal shift. So the shift value is considering from object to image. This shift is taken as here A dash. Here shift A dash which is equal to, that is, T into mu minus 1. This proof already we did in the previous video. Please watch part 3 video. Try to understand. Now light traveling from a rarer medium to denser medium bend towards the normal and extend the refracted ray which give the image corresponding to the object. So in case we are considering that mu A which is taken as mu dash. So instead of air, some other medium we are considering, for that refractive index is mu dash. Then the corresponding equations for the apparent depth. So apparent depth which is equal to mu divided by mu dash into real depth. Okay, and next formula for the real depth which is equal to mu dash by mu into apparent depth. Please try to understand. And corresponding apparent normal shift A dash which is equal to T into mu divided by mu dash minus 1. These are the equations when light traveling from the rarer medium to denser medium, that is object in the rarer medium and observer is in the denser medium. Because of here observer is very close to the rectangular glass slab. Now continuation we can discuss here this glass. Instead of that we are considering a rarer medium, air, okay, and denser medium is surrounding is taken as denser medium, that is mu m is equal to mu taken. So now considering this is the object O, okay, light releasing from the object which is incident on the glass slab. Okay, this is the glass slab. Actually the thing is here the rectangular glass slab made with the glass, but inside completely that is air only. That's why we are considering as a rarer medium, that is empty, that is nothing but hollow rectangular glass slab. Okay, see, try to understand. When light traveling from the denser medium to rarer medium, it bend away from the normal. So actual direction is this and it bend away from the normal. Then we can take here, extend this refracted ray that give the image of the object. So this give the image. Okay, so here observer is observing. So observer is very close to the rectangular glass slab, here taken as a rarer medium. Already we did that explanation. Okay, so whenever light travel from the denser medium to a rarer medium, what will happen here? The apparent depth and real depth, the proof already completed. Now here the real depth formula. So real depth, which is equal to refractive index of denser medium into apparent depth. Okay, so now the apparent depth formula, apparent depth which is equal to real depth divided by refractive index, and apparent normal shift, that shift is from the object to the image, that is taken as here a double dash. Okay, here writing a double dash, this is the a double dash, then a double dash which is equal to t is the thickness and 1 minus 1 by mu. Okay, so then if this rarer medium is taken as a refractive index, mu a is taken as mu dash. If okay, then the equations will be changed. What is the real depth here? Real depth which is equal to mu divided by mu dash apparent depth. Try to understand here. Mu divided by mu dash, and from this apparent depth which is equal to mu dash divided by mu into real depth. Okay, so now here apparent normal shift a double dash, that is a double dash which is equal to t into 1 minus mu dash divided by mu. Okay, so this is the apparent depth and real depth, apparent normal shift of the glass slab. Continuation. Now we will discuss a velocity between the object and the image. See, already we know observer in a denser medium, the formula of the apparent depth which is equal to product of a refractive index and a real depth. Okay, see now, considering this is the denser medium, in denser medium there is a observer, he is observing the object O. Okay, see now the object distance is taken as x and it will give the apparent depth, that is image. So the apparent depth of the image which is equal to mu into x. See that the formula apparent depth which is equal to a refractive index into a real depth. Okay, so the formula XAP apparent depth which is equal to mu into a real depth is taken as x. The rate of change of displacement is called velocity. Now considering here the object O which is moving with a velocity v towards the observer, even image also move with certain velocity towards the observer. That v value, that is v apparent velocity, we have to find. Now the rate of change of displacement is called velocity. Velocity is equal to ds by dt. Here x apparent, which is equal to mu into x, and d by dt of x apparent, which is equal to mu common constant dx by dt, and the corresponding equation v apparent, which is equal to mu into v. Here the velocity of the image is greater than to the velocity of the object. Okay, so v apparent, which is equal to mu into v. Here the velocity of the image, which is multiply the refractive index with velocity of the object. Here mu is the refractive index of the denser medium. And next case we are going to discuss now the observer in a rarer medium and object in the denser medium. Try to understand the basic formula whenever observer in rarer medium and observing the object in the denser medium, that is apparent depth, which is equal to real depth divided by refractive index. Okay, so here apparent depth is taken as x app, which is equal to real depth is taken as x divided by refractive index. See, here the observer is moving with a velocity v, observer, and image also move along the same direction. That velocity is taken as v app, apparent velocity. The rate of change of displacement is called velocity. Based on that formula, here the velocity of the image, that is v apparent, which is equal to v divided by mu. One thing remember, here the velocity of the image is less than to the velocity of the object. Try to understand. This is the explanation when the object in the rarer medium and denser medium observer and the velocity of the image is greater than to the velocity of the object. Here the observer in the rarer medium and object in the denser medium, in this case the velocity of image is less than to the velocity of the object. Here that is v app, apparent velocity, which is equal to real velocity divided by a refractive index of the medium. And examples we will discuss now. A ray of light refract from medium 1 into a thin layer of medium 2, crosses the layer and is incident at the critical angle on the interface between medium 2 and medium 3 shown in figure. If the angle of incident of a ray is theta, the value of theta is. According to the given question, light is traveling from the rarer medium to denser medium. See, this is the rarer medium and this is the denser medium. The reason is refractive index here is less, here refractive index is more. That's why here second medium is taken as denser medium, first medium is taken as a rarer medium, again third medium is taken as a rarer medium only. With respect to second medium, third medium refractive index is less. That's why here third one is also taken as the rarer medium. Try to understand. Now the light is traveling. This is the light, incident light, which is making an angle theta with the normal This is the normal, this is the incident ray. When light traveling from a rarer medium to denser medium, it bent towards the normal. So this is bending of light. Here we can consider R is the angle of refraction. See here, R is the angle of refraction. When light is traveling from the second medium to third medium, here angle of incident which is equal to critical angle. See, so R is equal to, we can consider incident angle. So because of opposite angles are same, that is equal to critical angle, and angle of refraction R1 is taken as 90 degrees here. Because of the light is traveling from the denser medium to rarer medium, the angle of incident is greater than to the critical angle, then the ray get reflected into the same medium. Okay, but here the ray is exactly grazes the second medium and the third medium. That's why here the ray is taken like this. Of incident is equal to angle of critical, then angle of refraction is 90 degrees. Then here this is the normal, see, and this is the ray which is grazing the surface separation of the both medium second and third. Okay, so we can consider this is the normal. Okay, so according to the Snell's law, here Snell's law, applying mu1 sine theta which is equal to mu2 sine r. See now, sine theta divided by sine r which is equal to mu2 divided by mu1. Here sine theta divided by sine r which is equal to mu2 value is 1.8 and mu1 value is 1.6, and again applying Snell's law from the second medium to third medium. Here mu2 sine r which is equal to mu3 sine r1. Try to understand here, sine r which is equal to mu3 divided by mu2 sine r divided by sine r1. So this is sine r divided by sine r1 which is mu3 value is 1.3 divided by mu2 value is 1.8. This is equation number 1 and this is equation number 2, and equation 1 into equation 2. So now we can write equation 1 into equation 2. Try to understand the values. Sine theta divided by sine r into sine r divided by sine r1 which is equal to mu 2 value is already I wrote 1.8 divided by 1.6 into 1.3 divided by 1.8 get cancelled, sine r get cancelled, but r1 is equal to 90 degrees because of r is equal to c. Then sine theta divided by sine 90 which is equal to 1.3 divided by 1.6. From this equation sine 90 is equal to 1. So sine theta which is equal to 13 by 16 and theta which is equal to sine inverse of 13 divided by 16. Second example, how much water would be filled in a container of height 21 centimeter so that it appear half-filled to the observer when viewed from the top of the container. Here refractive index of water is given, that is 4 by 3. Try to understand. According to the given question, the values are here h dash is equal 21 by 2 is given, and h is the actual height of the container that is asking. Then rarer medium is mu a is equal 1 and refractive index of water is 4 by 3, that is taken as a denser medium. Try to understand. Here the real depth is equal to apparent depth into refractive index, and the apparent depth is equal real depth divided by mu. So the apparent depth is taken as here h dash, which is equal to h by mu. Here h dash value is 21 by 2, which is equal to h divided by mu. Refractive index of water is 4 by 3. Now 21 by 2 into, that is 4 by 3, which is equal to h. Once twice get cancel, and this is 7. So h is equal to 7 into 2. So h is equal to 14 centimeter is the answer. Okay, thank you.